In a reversible process, the system and its environment can return to exactly the same states they were in by following the reverse path on the P versus V diagram. But there are irreversible processes too. An irreversible process is one that depends on your path on the PV diagram. If the process can go only in one direction, then the reverse path differs fundamentally, and the process cannot be reversible. So the second law of thermodynamics tells us that heat transfer occurs spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse direction. So for the second law of thermodynamics, it says that our heat can only transfer from a reservoir of high temperature to a reservoir of low temperature. And you will never have heat transfer from a reservoir of low temperature to one to high temperature. Okay, so this graphic here is this example. We've got a reservoir of hot material, cold material. Our heat is always going to transfer from the hot material to the cold material until they're in equilibrium. Another way you can state the second law of thermodynamics is by saying that isolated systems spontaneously evolve towards the state with maximum entropy. Entropy is a quantity that tells you about the disorder of the system. So systems will always evolve towards the state with more disorder rather than the opposite way around. And we kind of experimented a little bit with entropy in lab, where we talked about the coin flips and how we can change the entropy of a system by going from a state that has really high order, all heads, let's say, of a coin toss of 3, to a system that has high disorder, which would be a system that has a different number of heads and tails. You can also think about entropy by thinking about a coffee cup. Here's my coffee cup here. Right now, it's in a system of high order. All the bits are arranged to create this beautiful coffee cup shape. But if I break it, it is going to break apart into a million different pieces. I'm going to increase the entropy of my system. And it's going to be impossible for that system to somehow spontaneously arrange itself so that all those bits would be aligned back again perfectly to create the coffee cup that I started with. And yet another way you could describe the second law of thermodynamics is by saying that it is impossible in any system for heat transfer from a reservoir to completely convert to work in a cyclic process in which the system returns to its initial state. So it's impossible, what this is saying right here, that it's impossible for you to have a perfectly efficient engine. And now we're going to think about the second law of thermodynamics as applied to an engine.
Well, let's talk theoretically about how an engine works. Okay, so here is my schematic of an engine. Our engine right here, this is the thing that's doing mechanical work. Okay, this engine receives energy, QH, right here, from a hot reservoir. So let's imagine that our engine is a steam engine. From the hot reservoir, we've got steam here, and that steam is going to come in here, and that's going to cause, let's say, a piston to move up and down. It's going to cause that piston to do some work. Okay, so my engine is going to do work here, but it's also going to expel energy, what I'm going to call QC here, to the cold reservoir. So let's say my engine is doing work here, my pistons are moving, but eventually that steam is going to start to condense. And so we're going to expel energy to our colder reservoir down here. Okay, so in this process, work is being done. We've got energy coming in from my hot reservoir, doing work, and then the engine is expelling some energy to our colder reservoir. Okay, so the engine is absorbing energy, QH, from the hot reservoir. It does work, and it gives up energy to the cold reservoir down here. Now, this system is going to go through a bunch of cycles, okay? It's going to go through a bunch of cycles of this engine, taking QH, converting it over down here into QC, so now it's going to come back around again. It's going to be a cyclic process. And it's always going to return to its initial thermodynamic state up here to start this whole cycle again. So if it's always returning to its initial thermodynamic state, its initial and its final internal energies are going to be equal. So our change in the internal energy in the system is always going to be 0 when we're having the cyclic process here, okay? But then if we think about our first law of thermodynamics here, it says that our change in internal energy has to equal the heat minus the work done. This is the total heat in the system minus the work done in the system. If our change in internal energy in this case, because we have a cyclic process, is 0, then this equation tells us that Q has to equal work. Remember that this Q is the total heat in our system. It's going to be the heat coming from the warm reservoir minus the heat that's going into our cold reservoir. And that has to equal the work done by our engine, okay? So this is what's happening here in our theoretical engine. And if this working substance is a gas, let's say we've got, here we were talking about our steam engine, so we've got water vapor, okay? So if the working substance is a gas, then the work done is the area enclosed by a PV diagram if we were to model the pressure and volume of the system as it's going through this cyclic process. We can quantify the efficiency of our engine, E, we'll call it E here, and that efficiency is equal to the work that our engine does divided by the energy that the engine receives from the hot reservoir. We also showed that the work done by our engine is equal to the energy it receives from the hot reservoir minus the energy it expels to the cold reservoir. So we can write this as QH minus QC over QH, okay? So you can always quantify the efficiency of an engine if you know the energy it receives from the hot reservoir and the energy it expels to the cold reservoir. It turns out that it's impossible to have a 100% efficient engine. The best that we can do are engines that we call ideal engines, or they're sometimes called Carnot engines, okay, spelled C-A-R-N-O-T. In these ideal Carnot engines, the energy that the engine expels to the cold reservoir divided by the energy it receives from the hot reservoir exactly equals the ratio of the temperature of the cold reservoir over the temperature in the hot reservoir. Okay, now this only works for our special case of an ideal engine or a Carnot engine. So the majority of engines, this situation will not apply. Now this here is the PV diagram for our Carnot engine, the ideal engine, okay? So in a Carnot cycle, let's imagine that our engine is a piston that is filled with gas, okay? So here is my piston. Inside here, it's filled with gas, okay, little gas particles, and this piston is going to move up and down, okay? And that's the engine that we're going to be talking about here. In a Carnot cycle, there are two processes. You have two isothermal stages, and you have two adiabatic stages. In the first step of our Carnot cycle for an ideal engine, we are going to input energy to the system, but we're going to maintain our system at a constant temperature. So this is an isothermal process. And during this isothermal process, we start here at high pressure, low volume, and then when we input energy or input heat but maintain temperature, when we do that, we end up over here at a lower pressure and a higher volume. So in this step of the process, we are going to input heat. Our temperature is going to remain constant. Our volume is going to increase, but our pressure is going to decrease. In the next step of the cycle, this is what we call adiabatic expansion. Adiabatic means that the heat content remains constant. So Q is constant, but during this process, even though Q is constant, we are going to decrease our temperature from the temperature of the hot reservoir to the temperature in the cold reservoir. So temperature is going to decrease, and during that process, if we decrease the temperature at constant heat, adiabatic expansion, we're not inputting any heat into the system, or we're not losing any heat to the system, then we go from a system where we have a high pressure, low volume, to a system where we have a lower pressure, higher volume. So our pressure in this case is going to decrease, but our volume is going to increase. So that's our adiabatic expansion. So the expansion part, our gas is going to increase in volume. It does that, the pressure decreases if our temperature is also decreasing, but there's no heat input into or out of the system during that cycle. Okay, the heat remains constant. In the next step of our cycle, this is going to be another isothermal process. This process happens along an isotherm. Okay, the temperature remains constant, but in this step, now heat is going to be expelled from our engine. Okay, so Q is going to decrease, and during this isothermal process, if Q is going to decrease, then our volume we see is also going to decrease, but our pressure is going to increase right here. And then finally, we have the final step, or the final stage in our Carnot cycle to complete the cycle and come back up here to where we started. And that's going to be another adiabatic process. And we call this process adiabatic compression. Okay, so during this stage, again, Q is constant here, but during this adiabatic compression stage, our temperature increases from the temperature of the cold reservoir to the temperature of the hot reservoir. So T goes up, and as we do this, if T goes up, Q is constant, we are going to compress the gas in our system, in the piston here, and so we are going to decrease in volume, and as we do that, our pressure has to go up. Okay, so this is the Carnot cycle, the cycle that's happening in an ideal engine, and we always get back to where we started from in this cycle by going through two steps that were isothermal and two processes that were adiabatic. And we saw when we were looking at the PV diagram for our Carnot cycle that the engine is going to do work. It's going to do work because we know that, we saw this previously, that work is equal to the pressure times the change in volume. So we saw when we were changing pressures, we were also changing volumes. So the engine, not we, but the engine was doing work in that process. Okay. So the Carnot cycle, again, is for a perfect engine, an engine that achieves the best efficiency you can possibly have. Now we're going to think about the efficiency of a non-ideal engine, which is, you know, a real-world engine. Okay, so we have an engine that during one cycle, our engine extracts 2 times 10 to the 3 joules of energy from the hot reservoir, okay? And it transfers 1.5 times 10 to the 3 joules to the cold reservoir. As it does that, it is doing work. The engine is doing work. We want to find the thermal efficiency of this engine, okay? We don't have an ideal engine, we have a real-world engine, so the efficiency of this engine is going to equal the work the engine does divided by the energy that the engine extracts from the hot reservoir. We saw over here that the work that the engine does is the energy it receives from the hot reservoir minus the energy it expels into the cold reservoir divided by the energy from the hot reservoir, okay? And we can also rewrite this. This is also exactly the same thing as saying that this is equal to 1 minus QC over QH. How do we get that? Well, we can write this fraction like so. QH over QH minus QC over QH. And QH over QH is 1. So you can write this as 1 minus QC over QH as well. Okay? So then the efficiency of our engine is going to equal 1 minus 1.5 times 10 to the 3 joules divided by 2 times 10 to the 3 joules. And this is equal to 0.25 or 25%. So our engine here is 25% efficient. So what this is saying is that the work that our engine does is 25% of the energy that it's receiving from the hot reservoir. Now for part B, we want to find out how much work does this engine do in one cycle. That work is just going to be QH minus QC. So that is 2 times 10 to the 3 joules minus 1.5 times 10 to the 3 joules. That's 5 times 10 to the 2 joules, or 500 joules. That's the work that our engine does in this process. Then for part C, how much power does our engine generate if it goes through 4 cycles in 2.5 seconds? So here we found the work that our engine does in one cycle. If we want to find the power that our engine outputs in 4 cycles, we have to take that work and multiply it by 4. So 4 times the work that our engine does in one cycle divided by the time it takes to go through 4 cycles, which was 2.5 seconds, that gives us the power that our engine generates, which is 800 watts, because a joule per second is a watt. Remember earlier we were talking about an ideal engine, a Carnot engine. Only in that case can you say that the heat expelled by the engine divided by the heat input into the engine equals the temperature of that cold reservoir divided by the temperature of the hot reservoir. So the hot reservoir would be up here where the heat is being input into the engine, or the energy is being input into the engine from. And our cold reservoir is the reservoir where our engine is expelling some energy. And the temperature over here in this reservoir where the engine is expelling energy is always less than the temperature up here in the reservoir where our engine is getting energy from. Okay? So only in the ideal case of a Carnot engine can you say that QC over QH is equal to TC over TH. And so we weren't told what the temperature of the cold reservoir and the temperature of the hot reservoir was. But we know that for this particular engine, we would not be able to satisfy this ratio, that QC over QH is equal to TC over TH, because it's not an ideal Carnot engine.